So we've looked at a few different types of reactions, and what we're going to look at in this case is a special type of reaction or set of reactions, and that deals with aqueous solutions and reactions that happen with substances that are dissolved in water. So this is important because water is the most common liquid solvent on Earth, and it's the primary chemical component in living things. And so most chemical reactions involving biological things involve reactants that are dissolved in water, or at least very, very common to happen here. So chemical reactions that do involve reactants dissolved in water are among the most common. And so whenever we talk about these types of reactions, we need to remember back to something that we said back in the chemical nomenclature unit, which is that when we talk about substances which are dissolved in water, we don't really classify them in terms of our phase notation, in terms of solid, liquid, or gas, but instead we say they're an aqueous solution, sort of a special name that's given for substances dissolved in water, of course in water because it's aqueous. Remember that we indicated that at the end of a formula name by using that AQ symbol, that AQ notation. And so if we were trying to write out, remember, salt water, to show that salt was dissolved in water, or sodium chloride in water, we'd write it out with that AQ, indicating that it's an aqueous solution. And so looking at reactions in aqueous solution are sort of the ones that we're going to be talking about here. So, not all substances, when you put them in water, however, dissolve. And so, whenever we do a chemical reaction between water-soluble reactants, that is, between reactants that are in aqueous solution, if they produce a substance that is not soluble in water, that insoluble product will separate from the solution, forming a precipitate. Is the term that we use here. And so a precipitate, looks like it spells precipitate, but usually pronounced precipitate, is basically a substance that is a product of a reaction that separates from solution, does not dissolve, and so sort of falls to the bottom. And so we can see a little bit of that in this picture over here on the right, is that we've got a reaction that's produced this bright red compound, and instead of staying dissolved in the water, you can see it starting to form little crystals or starting to fall out. Oftentimes if you do a reaction that produces a precipitate, it almost looks like little snowflakes that sort of fall out of the reaction and settle to the bottom. Sometimes you don't even notice them. All of a sudden, you do the reaction, next time you look at it, and you see these little crystals all sort of collecting at the bottom like that. They have precipitated out. This type of reaction, which can be any of the other sort of types of reactions we talked about before in terms of single displacement, double displacement, things like that, but any of those types of reactions that form at least one precipitate are called precipitation reactions. And so, in general, we'd say that a precipitation reaction produces a precipitate, or a precipitate that's produced is the insoluble compound formed in a precipitation reaction. Now, that doesn't necessarily mean that all of the products in the precipitation reaction will be precipitates. You might have two different products that are formed, one of which is soluble and stays dissolved, and one of which is insoluble and falls out of solution as a precipitate. That would still be considered to be a precipitation reaction. It also is, of course, possible that you could have a reaction that produces two products, both of which are insoluble and both of which precipitate out of the reaction here. So it could be both, but if there's at least one precipitate that occurs, then we do consider it to be a precipitation reaction. Now, identifying which substances are going to precipitate out, that is, which ones are water soluble and which are not water soluble, can be pretty complex. Now, we already know a couple of general rules here, and that's that, a polar solvent like water, remember water is H2O, it's got its hydrogens that are not nearly as electronegative as the oxygens, and so it forms a polar covalent bond as those electrons all sort of end up on that oxygen, get that partial negative on this side, that partial positive on this side. You remember how those sort of worked here? That polar substance like water will tend to dissolve ionic substances and other polar substances. That like dissolves like rules, but it doesn't tend to dissolve nonpolar substances. So this is sort of our general rule. But even nonpolar substances will slightly dissolve in water oftentimes. And so if we take this into account, as well as some other factors that can also make a difference in terms of whether or not things dissolve, we can establish a set of rules that will tell us if a compound is soluble or not for the most common cations and anions whenever they are placed in water. And so let's take a look at these rules here. And so these are basically solubility guidelines that will establish whether or not the type of compound that we're discussing is going to be soluble, it either completely dissolves or almost completely dissolves, Whether it's insoluble, that is that it either none of it dissolves or almost none of it dissolves, or it's sort of in the middle here, and so that's what we talk about, these slightly soluble compounds. Those are ones that a little bit will dissolve, but not all of it. And so you would expect that anything that falls in the soluble category, if it's a product, then it's not going to form a precipitate. It would stay dissolved. If it's insoluble, it will definitely form a precipitate if you have a product that's an insoluble compound. And if it's slightly soluble, then it may form some precipitate, but not much. Most of the categories we're going to run into in this class are going to either fall into the soluble or insoluble categories here. We won't see a whole lot in the slightly soluble, but we just need to sort of discuss that those do exist. So let's look at sort of our rules here. We're first going to look at cases where it's usually soluble and only sometimes insoluble, and that's what we're seeing on this slide. So first rule that we have here is that if it's an acid, it's going to be soluble in water. And so that's straight up. So if you see an acid, you know it's going to be soluble right off the bat, not going to form a precipitate. Alkali metal salts. And so we say a salt, we're basically meaning a substance that usually is made up of an alkali metal as the cation, and then some other substance or some other ion or element as the anion here. So, for example, is a classic example of an alkali metal salt is NaCl. Is that because Na, sodium here, is an alkali metal, and so because of the fact that it has sodium as its cation, that is an alkali metal, this is our alkali metal salt, the whole thing. And so that would be soluble because alkali metal salts are soluble in water. Next one we have here are ammonium salts. And so we say ammonium salts, we're basically talking about compounds that have ammonium as a cation. So if the cation is ammonium, it's going to be soluble in water. Next one, we have several different lists here. So nitrates, acetates, chlorates, and perchlorates. And so this could be any cation with an anion that's a nitrate, any cation with an anion that's an acetate, anyone with a chlorate or anyone with a perchlorate. And so if you ever see something that says that it's going to be, let's say, I was going to say potassium chlorate, but that would be doubly because it's an alkali metal salt because potassium and it's a chlorate here. But let's say something like, I don't know here, aluminum chlorate. So aluminum chlorate, aluminum is not going to be hydrogen, so it's not an acid. Aluminum is not an alkali metal, it's not ammonium, but because it's a chlorate, it's aluminum chlorate, then it would be soluble. All right? So next one we have here, fluorides. And so any compound where fluorine is the anion is soluble, with the exception of these guys right here. So magnesium fluoride, you can see the Mg2+ ion right here, that's our cation. So if we had MgF2, would that be soluble? The answer is no, that is not soluble because of the fact that it is a magnesium is the cation of the fluoride right here. Calcium fluoride is not soluble, strontium fluoride is not soluble, barium fluoride is not soluble, and one of the lead fluorides, if you remember that lead has two possible oxidation states, it can be +2 or +4. If it's lead-2 fluoride, that particular oxidation state, then it's not soluble. Lead-4 fluoride, however, would be soluble. And so that's the only one you sort of have to be a little careful about to make sure you have the right ion for it, to determine if it's soluble or not. Next one we're going to look at is chlorides. So chlorides, bromides, iodides. So these are any substances where the anion is chlorine, bromine, or iodine. Those are all soluble with the exception of silver chloride, silver bromide, silver iodide, and then lead iodide, or lead-2 iodide specifically, is also not soluble. However, slightly soluble would be lead-2 chloride and lead-2 bromide. And so those can be soluble just a little bit in water here. And then last one that's sort of on our list of ones that are primarily soluble are going to be sulfates. Most sulfates are soluble with the exception of that strontium sulfate is not soluble, barium sulfate is not soluble, and lead-2 sulfate is not soluble, where calcium sulfate is slightly soluble and silver sulfate is slightly soluble. So you're not going to be expected to memorize these rules, but you will be expected to apply them if I give you the set of rules here. So, don't think that you have to know these off the top of your head. I don't expect you to remember all these sort of exceptions in here. Just that if I give you a list like this, that you should be able to identify whether a substance is going to be soluble in water, insoluble in water, and use that to figure out whether a precipitate will form or not. So let's look at the cases of ones that are primarily insoluble. So do notice that I've sort of flipped The 2 here is that instead of having be soluble and then insoluble, is now this is our insoluble one. This column is going to be soluble. Slightly soluble still sitting over here. So substances that are primarily insoluble. Hydroxides and oxides are almost always insoluble, with the exceptions of alkali metal salts. We talked about that before. So if I had something like K2O, like this, is that normally, since O indicates this is potassium oxide, would be an oxide, it would be insoluble, but because the cation is an alkali metal, then we would say that it is going to be soluble, so that's an exception to the rule. But if we had, let's say, Al2O3, aluminum oxide, because aluminum is not an alkali metal, is that this aluminum oxide would be insoluble because it's an oxide. Hydroxides, of course, work the same way. Now, the other ones that are soluble, that are hydroxides and oxides, are ammonium salts. And so if you had ammonium hydroxide or ammonium oxide, that would be soluble. And barium. So barium hydroxide, barium oxide is soluble. Whereas calcium oxide and calcium hydroxide and strontium oxide and strontium hydroxide are only slightly soluble. Next level we have here are ones that are also not likely to be soluble, typically insoluble, are carbonates, phosphates, and arsenates, with the exception of, similar to last time, alkali metals and ammonium salts. So anything carbonate except for an alkali metal carbonate, like sodium or potassium or lithium carbonate. If it's not one of those, then it would be insoluble. If it is an alkali metal as the cation or ammonium as the cation, then it would be soluble. Last one we have out of all these is sulfides. So if I had, like, for example, silver sulfide, Ag2S, that would be insoluble because the only soluble sulfides are alkali metal, alkaline earth metal, and ammonium salt. So Ag2S would be insoluble. However, if I had potassium sulfide, would be soluble. So it's insoluble, would be soluble because it's got an alkali metal up here. If I had barium sulfide, that would be soluble in water because barium is an alkaline earth metal as the cation. And if I had ammonium sulfide, NH4,2S right here, that would be soluble because even though it's a sulfide, is that it has ammonium as the cation right here. And so those are our general rules as far as solubility. So let's answer a few questions. Which of the following are likely soluble in water? So our first one is AlCl3, so aluminum chloride. So let's look back and look for, do number 1, we see any aluminum as one of the rules, and do we see a chloride as one of the rules? So I'm going to go back to our beginning here. So for the soluble ones, aluminum chloride is not an acid. Aluminum is not an alkali metal, so it's not that one. It's not ammonium, it's aluminum. So then we look at aluminum chloride. So it's not a nitrate, not an acetate, not a chlorate. This is a chloride, not a chlorate here. It's not a fluoride. Oh, here's chlorides right here. And so it says that, so we had aluminum chloride, so it says chlorides are typically soluble, but let's see if aluminum is one of the ones in the exceptions. So silver chloride is not soluble. Lead 2, that's not even a chloride, right in here. And then in slightly soluble are both lead compounds. So we would say that because it doesn't have one of the exceptions, that therefore that we should say this should be soluble, and so we would say this is soluble. I can't spell right today. S-O-L-U-B-L-E. Let me try to spell that right. So it is soluble for this one right here. All right, next one, Ga2S3. So we're talking about gallium sulfide. So gallium sulfide. So let's look back over our rules here. Is that it's not an acid. Gallium is not an alkali metal. It's no ammonia in here. It's gallium sulfide. So that's not nitrate, acetate, chlorate. No sulfide here, no sulfides here. These are sulfates, but we need gallium sulfide. So we go to the next set of rules where we say the insoluble. So hydroxide is not one of those, not an oxide. It's gallium sulfide, so not carbonate, not phosphate, not arsenate. Here's sulfides right here. And so sulfides are typically insoluble unless gallium fits into one of these other categories. So insoluble unless it's one of these other categories. So gallium, you look at the periodic table, is not an alkali metal. It's not an alkaline earth metal, and it's not ammonium. And so because of that, we would say that this gallium sulfide is going to be insoluble. Okay, so we got that right there. Next one we have here, K2CO3. So potassium carbonate. So we look back at the beginning. Is it an acid? No. Potassium carbonate is an alkali metal salt. Yes, it is. Potassium is an alkali metal. And so right off the bat, there are no exceptions to this. It tells us it's going to be soluble. And so for this one, we'd say it is going to be soluble. Now, I want to show you something. What if we hadn't noticed that? What if we just look for the carbonate on the end here? Let's look at the carbonate rule. And so it tells us here that carbonates are usually insoluble, but with what exception? If they have alkali metals as the cation. So since this one right here does have potassium, which is an alkali metal as the cation, then it sort of goes against, it's the exception to the rule that carbonates are typically insoluble. And so that's the reason why we'd say that's soluble. Next one, H3P. Well, that would be hydrophosphoric acid, or hydrophosphoric acid. And so we look back here, first one, all acids are soluble. And so this one is going to be soluble right here because it's an acid. Last one, NH420. So that's ammonium oxide. Looking back to our beginning here, is that it's not an acid. Ammonium's not an alkali metal. NH4, though, is ammonium that is going to show up here. So ammonium salts are soluble, and so even though there's no rules that say any exceptions to this right here, double checking, since it's ammonium oxide, it tells us that oxides are insoluble except for what? Ammonium, and this is ammonium here. So we would say that since the ammonium rule works out here, and it's the exception to the oxide rule, this would also be soluble. So that's sort of our rules for figuring out solubility. And so what this would tell us is that if we had a reaction that produced AlCl3, then it would stay in solution. It would not be a precipitate. If we had a reaction that produced gallium sulfate, then it would produce a precipitate because it's insoluble. If we had a reaction that produced K2CO3 or H3P or NH420, they would not produce a precipitate because of the fact they're all soluble. They would stay dissolved in water.